All right. Good afternoon, everybody, or good morning or good night, depending on where you are. Welcome to the latest IRIS Core Program webinar. This is your host, Andy Forsetto, the IRIS Swiss Army knife, who is located at the IRIS headquarters office in Washington, D.C. If you're not familiar, the Incorporated Research Institutions for Seismology, aka IRIS, is almost a 30-year-old consortium of universities and an NSF-funded science facility that operates programs which enable Earth scientists to perform advanced research in a variety of fields, particularly geophysics and seismology. And today's research-focused webinar was solicited to highlight scientific results either directly enabled by IRIS or representing important work from one of our partner organizations. And in particular, some of the work we'll be seeing here today was enabled by the IRIS Portable Seismology Program, which is centered in Socorro, New Mexico. Webinars like this are recorded and they are archived on IRIS's YouTube channel. And so I have that prominently displayed on my desktop. So that's right here, youtube.com user IrisENO. So if you search this on YouTube, you would find this page with all of the video content that's available. Lots of animations, lecture series, shorter lectures, long lectures, and of course the webinars. So this is being recorded and will be available in perpetuity from here. The webinar ground rules, just so everyone knows, only the presenter and I are going to be the speakers. If you have a comment or a question as the webinar is going on, then you should please clearly and concisely type it into the box on your control panel. So about halfway down, you should see a box called questions, and you can submit that there. I will receive that, and I will read those at the end during the Q&A. I'll read your name as well as the question to Berk. And if there are similar questions that are asked throughout the webinar, I might try to condense those all into one question, or I may skip some that are just redundant. If the webinar crashes, which happens on rare occasion, I can reboot it. So you just need to sit tight for a minute and then click the same link that you got when you received your registration email for this, and it should bring you right back in there. And then, just for my benefit, I like to know if it's more than just you watching at your computer. I have the names of each unique user that's registered, but if you're with a group, it really helps to know if you have, +5 hanging out watching as well. So, without further ado, I want to introduce our speaker today is Dr. Berk Biryol, who is a postdoctoral research at the University of North Carolina in Chapel Hill. And just as a fun historical anecdote, in 2004, there were two grad students that joined Susan Beck and George Zand's Seismology and Tectonics Research Group at University of Arizona. Berk was one, and I was the other. So it's really exciting to have Berk today giving our IRIS webinar. Just a little bit of background on Berk. He received his master's in structural geology from Middle Eastern Technical University in Ankara, Turkey, and he received his PhD from Arizona in 2009. I've known about the cool work that Berk's been doing in the Eastern Mediterranean Turkey area for years, so I'm excited to be able to convey that to you guys. So without further delay, here is Berk to present a snapshot of Eastern Mediterranean lithosphere and upper mantle, clues to the demise of the Tethys Ocean. And Berk, I am going to shift this over to you, and I'll make sure that you're unmuted, and it'll take just a second. Okay, you should be good to go, Berk.
All right. Thank you very much, Andy, for the very nice introduction. So I'll just shift my display. Probably you can see my display right now, right?
Okay. It looks like it's in presenter mode, Berk.
Oh, hold on a second.
There you go. No, now it looks good.
All right. I'll go back. Is it okay now?
It's perfect.
All right. So thanks for the very nice introduction, Andy. And hello, everyone. Thanks for giving me the opportunity to present our results here. And this presentation focuses on our results that provide clues about the structure and evolution of Anatolia and Eastern Mediterranean. And this holds clues for the demise of Tethys Ocean. My collaborators in the study are Susan Beck, George Zan, Jonathan Delve from University of Arizona, Arda Özacar from Middle East Technical University, and Linda Warren from St. Louis University. So Anatolia is a very complex region in terms of tectonic because it occurs in the collision front between Gondwana and Laurasia. And this complex tectonic layout reveals itself as being partitioned into 4 different tectonic domains with different characters of deformation experienced today. And basically these are the East Anatolian province, Central Anatolian province, and West Anatolian province, as well as the North Anatolian province. So the East Anatolian province is a contractional province. And this contraction is due to the northward indentation of Arabian plate into Laurasia margin. And this zone is characterized by a conjugate strike slip fault system as well as thrust fault systems. This collision and indentation resulted in westward escape of Anatolian plate along the North Anatolian fault zone and the East Anatolian fault zone. And the Central Anatolian province is characterized by splays of the North Anatolian fault and also characterized by diffuse seismicity compared to East and West, and also scattered volcanism in its central parts. The Western Anatolian province, on the other hand, is characterized by extension. And this extension is due to the slab rollback that's taking place along the Aegean Trench and northward Aegean subduction zone, which shows itself as a back arc extension in this region, actually. Another curious feature of this region is the Cyprus Trench and the Cyprus subduction zone, which is much more dormant compared to Aegean Trench. And there's not a clear pattern of seismicity associated with it. Of course, there is another key player in this picture, which is the Laurasia margin. And this margin is mainly composed of crystalline rocks and crystalline complexes of Laurasia margin, and generally reveals itself in form of fragments. One fragment being the Istanbul zone, which is more flatter region that you see here, and the other fragment being the Eastern Pontide zone, and these are basically called pontic fragments. Eastern Pontide revealing itself as a high topography at the coast of Black Sea. So, but this is not the complete picture of complexity. The Anatolian plate itself is a composite of various blocks. And the interrelation between these blocks are also very complicated. Towards north, for example, this central magenta colored block is called the Kırşehir block. The green one is the Torite Anatolite platform or Torite Anatolite block, which has a subdomain known as Sakarya block up in the northwest or up in the west. And also there is this curious feature known as the Sparta angle, and the name comes from the angular shape of this region defined within this southern part. And this region is characterized by very complex tectonics with various trends of faults and deformational features, and it makes up the boundary between the Western Anatolian province and the Central Anatolian province. So with all these variations and complexities, the characteristic crustal and upper mantle characteristics of this region has been always in question. And in order to address these, there have been a lot of permanent and temporary deployments out across the region. There have been more than 450 seismic stations deployed in the region in the past. And of course, I'm counting both short period and broadband deployments. But not only the complex characteristics of region is the key player. Also, the seismicity is an important reason why this dense network was deployed all around Anatolia. Western Anatolia particularly is one of the most seismically active regions in the Earth. And as you can see, there are lots of seismicity that took place in between years of 1900 and 2013 with magnitudes more than 4. And an important feature here is the North Anatolian Fault. As you can see, most of the major earthquakes with magnitudes larger than 6 took place along the course of the North Anatolian Fault. However, in terms of background seismicity, the Anatolian Fault does not come up as a distinct feature, although it has created destructive earthquakes in the past. And because of the advantages it provides to the people, like strike slip basins, well-drained strike slip basins open to agriculture and very fertile land, this region attracted a lot of population to the cities that lay around North Anatolian Fault. Basically, the cumulative population of all the cities around North Anatolian Fault is more than 24 million. This is 1/3 of the population of the country. So the latest destructive sequence of earthquakes took place in 1999. And this earthquake was a 7.4 magnitude earthquake and hit the city of Izmit, which is the industrial core of Turkey. And this damaged the Turkish economy greatly at that time. And also it's resulted in casualties and a lot of injuries. And it also showed Turkish people and the world that this region, where more than 20 million people lives right now near the city of Istanbul, is open to this sort of a hazard. And this is now in question when the earthquake will happen near Istanbul that would threaten more than 20 million people. So in the past, historically, the sequence of earthquakes progressed from east to west, starting from 1939. And for the case of North Anatolian Fault, this was always the sequence. There were earthquake cycles going back and forth along the fault in east or west direction. So now, after the 1999 earthquake, we expect an earthquake of magnitude 7, around 7, in the Istanbul region. And that's why in the map that I showed 2 slides before, there are lots of seismic stations deployed in this region in order to monitor the seismic activity closely near the city of Istanbul. So the North Anatolian Fault, the recent efforts reveal that the North Anatolian Fault follows the weakness zone defined by the Tethysite accretionary complexes and placed on the Anatolian plate also, and placed between Anatolian plate and Eurasian plate along this gray zone. And due to blocky composite nature of Anatolian plate, the accretionary complexes changes geometry along their trend, basically. And the North Anatolian Fault sort of, you can see, adapts itself to these geometrical changes. and exploits the weakness zone defined by the accretionary complexes. However, even though now the recent efforts revealed this, we are not yet clear about the lower structure of the North Anatolian fault, and particularly how wide is the shear zone associated with North Anatolian fault in depth. How does it look? How does it relate to this accretionary complexes and the structural features of those accretionary complexes in the wider zone? What's the deeper geometry of this shear zone? And is there significant difference between blocks to the north and south in terms of structure and composition? This is also true for the blocks that make up Anatolia. So the most important one of them is the Kırşehir block, which is actually located at the center, at the core of the Anatolian plate. And recent studies by Gans et al. In 2009, a PN tomography study, revealed that this Kırşehir block in uppermost mantle has distinctly different signature than the surrounding mantle, and this sharp variation occurs along this its eastern boundary, marked as the central Anatolian fault zone, which is actually an active fault, which also shows us that even in the case of Anatolian block, the suture zones between blocks are weakness zones for strike slip faults to run through and accommodate deformation. In the eastern part, it's already been well documented that the slab detachment associated with the collusion of Arabian plate into Laurasian margin resulted in uplift of Asthenosphere, or upwelling of Asthenosphere underneath the East Anatolian plateau, which now dynamically supports the plateau, which has a mean elevation of 2 kilometers, and also resulted in extensive volcanism in this region. So there are a few questions that needs to be addressed regarding the upper mantle structure of this region. Major one of those are how the Aegean trench is connected to the Cyprus trench, meaning that how this Aegean subduction zone is connected to Cyprus subduction zone in the east, and how they are related with the Arabian collusion front. How the scattered volcanism is controlled in this region, and what controls the mantle flow in this region, and how does it appear in a broader Tethysite accretionary framework. So in order to address upper mantle related questions, we carried out finite frequency tomography. And as you know, this is a teleseismic tomography, and we have distance earthquakes and arrivals signals coming from those distance earthquakes to our stations. And we measure how late or how early they arrive, and invert for the velocity structure underneath our station array. The finite frequency approximation in this framework helps us to improve our resolution by exploiting the frequency content of this signal that arrives to our stations that we pick. And this basically allows us to define a broader zone than the theoretical ray pad around our ray arrival, and helps us to sample our model volume much better. That's why these, because of their shape, actually these are called banana donut kernels. The sensitivity kernels are called banana donut kernels. So the data sets we used generally composed of teleseismic earthquakes between 39 and 90 degrees ranges, and also 100 to 180 degrees ranges. This helps us to sample our model volume as evenly as possible in all different directions. And here I'm showing some maps of model sampling, red color showing good sampling and blue colors showing poor sampling, and the diamonds showing the stations. By the way, the stations here are temporary deployments of Eastern Turkey seismic experiment, North Anatolian fault seismic experiment, and Kandilli Observatory Earthquake Monitoring Center's permanent stations across the region. So as you can see, at shallow depths, the sampling of the model is only limited to the locations where we have stations. This is a general problem of teleseismic tomography. Since our arrivals are pretty steep, closer to the surface, they don't intersect much, and they only sample the footprint of networks that we use. But below 100 kilometers depth, this sampling pattern evens out and provides much better sampling, as you can see in these maps. So another way to assess the resolution power of our data set is to run checkerboard tests. I'm pretty sure many of you know what these checkerboard tests are, but in order to explain simply, basically we have a model, synthetic model, and we introduce fast and slow velocity anomalies in an alternating manner. As you can see, fast velocity anomalies here are blue, and slow velocity anomalies are red. And these are embedded in a neutral background. And ultimately, what we are trying to do is we are trying to use our data set and retrieve these patterns back through tomographic inversion. And this is what you are seeing at two different depths using this approach, and the cross-section across the central part. And as you can see, our resolving power is good enough to resolve major structural features of this region. But we can also carry out some more realistic tests, which are called realistic synthetic recovery tests. And in those tests, we introduce slabs into our model, and using our data set, we try to retrieve them back. And in the uppermost panel, you are seeing the slabs that was introduced along the Cypress trench. And this is what we are getting after our inversion. This shows that the general outline of those slabs could accurately be retrieved using this approach and using this data set. So the resolution power of the data set is good enough to resolve it. And also, we are also identifying some limitations of the teleseismic tomography or our data set in the shallow parts, where, as you can see, their flat sections of slabs are not very well resolved, or not resolved at all, due to limitations intrinsic to the teleseismic tomography. So the major features that we identify in our study are these fast velocity anomalies associated with the Aegean trench and Aegean subduction zone, and the Cyprus subduction zone, these two anomalies. And we are identifying that these two anomalies are separated by slow velocity anomalies, this red pattern that you're seeing here. And as a third one, we are identifying some fast velocity anomalies at shallower depths on the northern block of the North Anatolian fault in its western section. We are also identifying slow velocity anomalies associated with the East Anatolian plateau in the east. So when we get cross sections, we can clearly see the Aegean slab subducting in a northward fashion along the Aegean trench. Further to the east, we are also identifying a western or a Cypress slab dipping northward in this region. We are also identifying a gap between these two structures, which is accommodated by slow velocity anomalies. And we were able to also identify that the edge of the Cypress slab is roughly the peak point of this zone of crustal structural complexity known as the Sparta angle. And also we are seeing the outline of these phase velocity anomalies down to depths of 100 kilometers to the north of the North Anatolian fault, this anomaly, which ends rather sharply at the fault, at the surface projection of this structure. So another curious feature is the Sparta angle, where our Cypress slab steeply starts to dip steeply into the mantle. And perhaps the outline and the steepness, also the rather discontinuous appearance of this Cypress slab suggests it's in the phase of detachment. In the shallow parts, however, our resolution is not very good to constrain what's going on underneath the Sparta angle and how this steepness coming from this trench is achieved later on. But recent studies by Jonathan Delph from University of Arizona revealed that this zone of complexity known as the Sparta angle is underlain by relatively slow velocity anomalies. This region is pretty complicated, and since Oligocene has experienced some rotations, both clockwise and counterclockwise in its western and eastern limbs. And Jonathan's results, ambient noise tomography results, revealed that the upper mantle associated with this zone is also rather complex. And we get anomalously slow velocities, S-wave velocities, underneath the Sparta angle. This zone does not have much of heat flow. It is less than 70 milliwatts per meter square. And hence, we believe, and there is some intermediate seismicity taking place, intermediate depth seismicity taking place underneath this zone. So we believe hydrated subducted fragments that are relatively shallower angle in this region might be responsible for the slow velocities that we are getting. So it sort of agrees with what we are thinking about this region, where there is shallow subduction that taking place beneath the Sparta angle, which also supports a Sparta angle dynamically and gives way to relatively higher topography and complex geometry in this region. And hence, we come up with this idea of evolution for the slab geometry in this region. We believe that major obstacles to subduction are encountered along the Cypress Trench. And the latest one being the Aristoteles seamount and Aristoteles fragment that occurs just south of the Cypress Island. And this one is where a Sparta angle is. And now there's fragments subducting, hydrated fragments subducting dynamically, hydrating the fracture zone in the crust, and shear zones in the crust, as well as the mantle above it. And sort of yields slow velocities in this region. So this obstruction of the Cypress Trench gave way to a differential rollback scenario in this region. Basically, Aegean Trench was allowed to roll back more freely than Cypress slab when these attenuated margin fragments of the African plate encountered. And then we had a displacement, which are generally called subduction transform edge propagators, commonly known in the Mediterranean region, which are associated with slab tears in the rest of the Hellenic system. So we believe these obstructions gave way to the terminal phase of subduction along the Cypress Trench, and now we believe Cypress slab is in the phase of detachment. That's why it's steeper, and at parts it's rockier. And perhaps the sequence of these obstructions were different, which gave way to other discontinuities along the strike of the trench and along the strike of the slab, like minor tears. One of these tears, this one, now underlies western Tauride mountains, basically this region. And this region experienced an uplift of 2 kilometers in the past 8 million years, which is a really drastic rate of uplift in this region. And we believe that tear and the asthenosphere that flows through that tear and placed beneath these ranges is responsible, partly responsible perhaps for the uplift, that rapid uplift experienced in this region. Even though we have pretty good coverage all throughout this region, we have some limitations associated with the central Anatolian plateau in terms of resolution, as I showed you earlier. So this is due to less coverage of stations present in this region. And now I'm showing you a map of a new deployment that we carried out this summer. And this deployment has more than 65 stations deployed in this region. And we believe this would help us constrain major questions associated with Central Anatolian volcanic field and Central Anatolian tectonic provinces, as well as slab geometry in this region, much better than our current results. So it will improve our results. So as I said, this summer we spent approximately 1.5 to 2 months deploying and getting ready for this deployment. These stations, which are more than 65, they will be there till one more year, basically. And we believe they can provide significant information. So what I'm showing you here is a synthetic test with and without the presence of this array. And in this case, these triangles show the earlier layout of stations. And you can see that if we input a synthetic pattern like this of slabs and slows, we are retrieving it like this, which is more smeared and poorly resolved. But we believe with the addition of this Central Anatolian tectonics deployment, we will be improving the resolution in the central parts and beneath Central Anatolia. So Kershare block is another curious feature, and our recent results from ambient noise tomography carried out by Linda Warren revealed that this block is distinctly different from the surrounding blocks of the region. And this block, with its crystalline rocks and crystalline complexes, appears much faster than the surrounding blocks of the Anatolian plate. And these differences tend to be very sharp along the boundaries of this block, namely the Central Anatolian fault zone out here, and the Tuzgeli fault zone and Tuzgeli system in the western part. So Linda's results also revealed slow velocity anomalies associated with the East Anatolian plateau, and also revealed relatively fast velocities or slow velocities at the shallower parts beneath the Central Anatolian volcanics, perhaps indicating presence of melts associated with the volcanic fields of Central Anatolia. And a broader and more detailed study by Jonathan Dell from University of Arizona also related very interesting results. So Jonathan model was able to resolve this curious slow velocity anomaly that is associated with the accretionary complexes of northern Anatolia. And at deeper parts, when we look at these accretionary complexes along this line of section, at deeper parts, they lose their signal, and actually the signal associated with these slow complexes are lost, and actually we gain normal values, which perhaps indicates that this is sort of a wedge that sits on the blocks of northern Anatolia and Anatolian plate-related blocks, and also the fragments of Laurasia or Eurasian margin up in the north of the North Anatolian fault. So we are also at depth seeing variations across North Anatolian fault, sort of clear variations in this region, which indicates that North Anatolian fault is a structure that clearly bounds, at least at its deeper parts, the geologic properties of north and south blocks, and separates them and juxtaposes them clearly at depth, showing its lithospheric scale characteristics or crustal scale characteristics. Also, as I mentioned earlier, Johnson's results showed slow velocities associated with the Sparta angle, and this region, which is basically a zone of complexity due to shallow angle subduction and obstructed subduction, as well as slow velocity anomalies associated with the Eastern Anatolian Plateau. And also, he was able to resolve a much different structure, which is the Arabian lithosphere. You see along this profile in this section, which is completely different than the accretionary material outlined as the Eastern Anatolian Plateau to its north. And in this respect, we believe the North Anatolian fault follows this suture zone throughout its course, at the deeper parts as well, and juxtaposes different rock units and appears as a clear signal in terms of seismic velocities across its across profiles taken perpendicular to it. And we believe these fragments play important role in delineating the crustal scale deformation associated with the North Anatolian fault, as revealed by Jonathan's results. So in order to address anisotropy-related concerns about North Anatolia and North Anatolian fault, we have carried out shear wave splitting analysis. And our splitting analysis for the NAF array, and these are the stations of NAF array, and the bars show the trend of the anisotropy observed from our results, indicates that there is a general uniform pattern of anisotropy, which is most probably indicative of deeper source for anisotropy rather than a crustal source for anisotropy. Also, we didn't observe any trends in our measurements that could be paralleling the North Anatolian fault shear zone, which could be indicating the crustal shear in this region. So we tried to model this using two-layer models for our anisotropy results, but we couldn't get conclusive evidence showing a shear zone that could be associated with North Anatolian fault. So although San Andreas fault and North Anatolian fault are generally considered analogous to each other, North Anatolian fault is much younger than the San Andreas fault, and the cumulative displacements, which are in the order of 7 to 80 kilometers, much smaller compared to cumulative displacements associated with the San Andreas fault. In this manner, We believe we are not seeing a distinct, clear signature like they see it in the case of San Andreas Fault here in North Anatolian Fault that could be associated with this fault-related shear zone. And perhaps this is because this fault is much younger and there's not enough time for a well-developed shear zone to come into existence in this region yet. So in a broader perspective, the general layout of shear wave splitting results all across this region is pretty uniform at its northern parts and eastern parts. However, as we go closer to the slabs resolved in our study, we begin to get variations from these regular trends, northeast, southwest trends. We believe the differential rollback rates taking place along Cyprus and Aegean arc might be responsible for the broad background anisotropy observations, but in a local sense, near the subduction zones, we believe the slab geometry being steep in the east and being relatively gentler in the west controls how mantle is flowing around it. And these regions in the box are from Pamir and Arda Özacar. And this is work in progress, and they are seeing clear variations from the general trends observed to the east and to the north in the central parts, which could be associated with the edge, slab edge related flow complexities for the mantle. So in summary, we believe the segmented slab geometry beneath Anatolia is due to differential rollback rates experienced between Aegean slab and the Cyprus slab. This which actually gave way to tearing of the slab, African slab, and our tomographic images clearly revealed slow velocity anomalies associated with these tears, and these anomalies underlaying the major volcanic centers of Western Anatolia and Central Anatolia in the sense. And also we are able to resolve well-documented slow velocity anomalies associated with the Eastern Anatolian Plateau. Our models also reveal the Tethyan lithosphere is laying flat on 600 discontinuity. And previous studies also, more larger scale studies also revealed that this is the case for entire alpine Himalayan system in Tethyan suture zone. So based on ambient noise tomography results, we were able to identify that Anatolia is actually all through its crustal structure distinctly different, composed of distinctly different blocks in terms of seismic velocities. And the shear zone and the suture zone associated with the Tethyan accretionary material at shallow parts a pretty clear signal, and NAF overrides this. And at deeper parts, the fragmented nature of the Laurasian margin, the pontic fragments, clearly reveals variations across NAF. But these are, rather than being displacement-related seismic variations or characteristic variations, these are, we believe, mostly related with fragmentation-related variations in the lower crust. And also for the case of the Sparta angle, we believe a shallow subduction due to subduction of attenuated African margin fragments might be taking place, which generally it's believed that the case for the subduction section of Cyprus slab around south of Cyprus Island. And we believe the hydrated fragments provides required liquids or fluids into the system here, which yields low velocities, anomalously low velocities for the Sparta angle and the uppermost mantle beneath the Sparta angle. So in terms of flow, we think differential retreat rates controls the flow pattern, background flow pattern in this region. However, as we get closer to the subduction systems themselves and the edges of the subduction, we see clear variations, which we believe are controlled by flow complexities that could be associated with slab control on mantle flow. So this pretty much sums up what I want to say about our findings, and I am hoping you enjoyed this, and I'm looking forward for your questions.
Great, thank you very much, Berk. That was awesome. So while the questions are submitted, I had one that was based on how helpful would constraints on the location of the LAB be in some of these interpretations, maybe particularly related to the volcanic centers? And is that something that you guys have been looking at?
Well, in the past, we tried looking at it using S-wave receiver functions, but S-wave receiver functions are generally tricky. So we definitely want to revisit our interpretations regarding S-wave receiver functions and also analysis. But I believe in terms of volcanics, in terms of Central Anatolia province, like block differences, putting better constraints on LAB is really important. And I believe the deployment of this CD-CAT project in the Central Anatolia could provide some important clues about LAB in this region, since this array is much better positioned and could potentially yield much better data sets compared to other limited data sets around the region.
Okay, great. Okay, we have a question from David Cornwell, and David says, "Very nice presentation, thanks. Do we know what makes the Istanbul so fast?" And then his follow-up question is there similar fast lithosphere beneath Ukraine and Crimea on the other side of the Black Sea?
Oh, that's a good question. Actually, I'm not sure about the other side. Thinking that this is a Berk basin that sort of opened up during the closure of the northern branch of Tethys. There's no reason not to think that there might be a counterpart of it in the Crimea part. But in terms of Istanbul zone, as far as I know, Istanbul zone is characterized by Precambrian basement rocks and crystalline rocks exposed on the surface too. And this is why it's much different than the rest, or, well, not the rest, but most of the central parts of the Black Sea coast. Eastern pontite fragment also shows similar characteristics, but it's all overprinted some volcanism associated with the collusion of Arabia and during that closure stage. In the central parts, however, we have a zone which is also, as you have seen from my previous maps. Maybe I can go back to that. That's a part of the accretionary complexes. So basically, this section of accretionary complexes separates the eastern pontites and the Istanbul zone. And I believe That's why the blocky appearance is really important, delineating the North Anatolian fault in deeper parts. And the fragments are of similar nature surrounding these accretion complexes in between them. I guess the short answer will be, I guess the complexity in the closure is an important factor that separates these two blocks.
All right, great. Next question is from Mike Taylor, and Mike says implicit is dynamic support of topography. Then he asks, what is the amplitude and wavelength of presumably whatever dynamic topography you're observing here?
For East Anatolian,
He wasn't specific, but I'm going to guess that, yeah.
yeah. So right at the top of my head, I am not sure about the wavelength, but as far as I remember, Sanger et al.'s paper from 2010, I believe, actually compares the Eastern Anatolian Plateau with Ethiopian Plateau, as far as I remember. So I think that might be a good paper to check for that matter. I believe that will provide more clear answers than what I can do here.
Okay. Next question is from Ling Chen, and Ling is asking, is there any geodynamic numerical modeling result in this region which might be able to provide mantle flow modes compatible with what you're observing seismically?
As far as I know, no. There are not any geodynamic modeling. Recently, there are not so geodynamic, but there are some modeling attempts by Arda Özacar's group in Middle East Technical University for a multi-layer anisotropic case for the upper mantle, which can give some idea about the flow directions and its variation with depth for the central Anatolia. But I don't think there exists a detailed geodynamical study that focuses on flow modes in this region.
Okay. Next question is from Yuri Shatner, and Yuri asks, he says, thank you for the very interesting talk. In one of the slides, there was a color change under Cyprus at approximately 60 kilometers depth. Given the westward motion of Anatolia, do you think it is reasonable that Cyprus is being compressed from east to west?
Interesting question. I guess this would be the figure. Well, as far as I know from the focal mechanisms in this region, there is no clear indication that it might be there might be a east-west compression or anything like that that might be present in this region in terms of Cyprus region, I believe. Yeah.
Okay. Well, unless there are any more questions, I'll let that hang for just a few seconds. If there's anybody typing one last one in, uh, I just wanted to thank you, Berk, for a
Thank
great
you.
talk and on a subject that we really haven't covered in any of the webinars yet. So doing something in the Mediterranean region was way overdue. So it was great that you were willing to do that. And I want to thank the audience and the speakers for attending and their questions. This has been recorded. I'll post it on YouTube after this, and it will be available for anybody who might be interested in this but missed out. And I feel obligated to point out that I just got a nice note from our from Berk, your former advisor, Susan at Arizona, that our geophysics program is now ranked number 8 in the country, which is
Yeah, I got
very
news
exciting.
today. Yeah,
So
great.
yeah, but anyway, thanks again, Berk,
Thank you.
and we'll see all you at the next webinar.